for extended Scan-to-BIM workflows. So to make it as understandable as possible, I will divide my presentation into 5 parts. In the first 3, I will give you a short introduction, and then we will move on to the experimental setup and text events. And third part we will be talking about the 3D reinforcement reconstruction. And the fourth part is about results evaluation. Finally, I will conclude my study. So first, for the introduction, is our motivation. So getting the BIM models from the existing structures has become more and more important in the field of civil engineering, but much research is focused on only in visible components. So there's not much in-depth research on steel embedded on the structure. So we will decide to use some devices equipped with the GPR technology to achieve the 3D reconstruction of the steel bars on the concrete. So the GPR technology means the ground penetrating radar. So the devices in our study we use 2 devices from this GPR technology. One is the Hoeh PS1000 and the other is GP8000 from ProSec. So the processing includes scanning. So we should first scan the plates, the concrete plates, and then we make data processing, and finally we make reconstruction. So I will introduce our experimental setup. So we have set up 2 test specimens with different size of rebars and also with different spacing of rebars. This is our experiment, and then we have covered it. After pouring concrete, we have covered it with grid paper, and then we scan these plates with our devices. These are devices here, the PS1000. Around this grid paper and around the roots set on this grid paper, then we can get the data from our device. So for the GP8000, our another device, there are many parameters we should set up for achieving more accuracy for our reconstruction. Here's the most important parameter of the many parameters is the permittivity of our this GP8000. So which can be determined by this tag of back face with envelope curve. And then I will try to introduce this 3D reinforcement reconstruction. So the main task of 3D reconstruction is to fit the 3D points to the corresponding geometric shapes. Geometric primitive. So for us we have not only measured the position of rebars manually, but also we have also scanned it used by the Leica scanner to create some point clouds of our of the rebars. Then we can get also the more accurate position of the rebars as the point cloud. So we also use this point cloud from the Leica scanner as the reference model. Then we can use this reference model to compare our results. To compare the correct position of the rebars with our scanned results. So it's also very important to fit our point cloud to the geometric shapes. So our rebars is naturally can be approximated as cylinder shapes, although I mean cylindrical shapes. So we then for the reconstruction of these point clouds, we use the method, also the famous method Renseik shape detection algorithm for our reconstruction of the rebars. So for the input parameters for this Renseik algorithm, we have also determined three important parameters. One is the minimum number of the support points, and the maximum distance from the initial primitive, and then is the sampling resolutions. And we have successfully fitted the number of our sample, the number of many rebars. I mean the correct number of the rebars. So during the processing, will also become some errors. So the first errors is intersecting cylinders. So there we have during the reconstruction processing, there's also some intersecting cylinders. There's also adjacent direction cylinders. So we to solve this problem, we have continuously test and adjust our parameters to get a much better results. I mean, to get more accurate results. So then I will talk about our results evaluation. So we have evaluated our results in terms of two fields. One is the diameter of the rebars. So we want to reconstruct the diameter of rebars correctly and use our two divisors. And this is one device is Hilti and the other device is Prosec. And by specimen 1 and specimen 2, there's many deviations from the Prosec. You can see the diameter from the brass is only 16, but there's 59. This is big deviations, and only by Hilti we get better results. And then the other, we want to evaluate the average distance of the rebar. So I mean, it's the correct positions of the rebars, and by these two devices shows effective results. I mean, this sufficient results. So in the end, I will conclude this study and to discuss our results. So firstly, our studies. In our study, here TPS 1000 provides sufficient accuracy of the rebar localization or rebar position, and this is suitable for the Scan-to-BIM workflows. And then, but diameter extraction is inaccurate for both devices, and Prosec GP 8000 is okay. It's also it performs also accurate, also well on location extraction, but it has less reliable diameter detection. So we cannot get good results on diameter extraction, but we can get effective results. I mean, suitable results for the BIM modeling in field of spacing. I mean, field of position. So even localization data alone, but it's also valuable for the structural case reuse. I mean, the rebars on the concrete is also very important for the life cycle assessments of the buildings and for the reuse of the building materials, structural components. So our future work will also focus on more accurate diameter detection, and so we also need to make some practical validation in real scenarios, and we also we will also, in our future work, we will also combine some marker systems with our grid paper to achieve the more accurate results. And in the end, in the future work, we will also research on comparing the efficiency of this GPR technology with manual modeling in terms of time and efficiency. So thank you for your listening.